Welcome to another EC&M Tech Talks. Today we're talking about terminology that we find in the National Electrical Code. Specifically some of those things that confuse us once in a while maybe because it's not very clear or there are different definitions that are very similar or whatnot. So anyway, we've got 7 different topics that we're going to take a look at. First of all, we're just going to start with Article 100, and we're going to look at the 2023 changes to the National Electrical Code in Article 100. We're going to talk about voltage levels, high voltage, low voltage, medium voltage, where we find that information. Cables, different types of cables. We'll clear up maybe a little bit of confusion about some of the terminology with cables. Circuit breakers and fuses, 2 separate topics we're going to talk about. Also the classes of circuits, and remember for the 2023 code we've got a brand new class 4 circuit we're going to talk about as well. And then finally we're going to talk about a few of the terms, a little bit about grounding and bonding them. So anyway, I've got on my electrician's hat today, and let's get started, okay? So first of all, in Article 100, now all terms, all definitions are in Article 100. There's no more .2 in the different articles. All of that, those .2 terms have been moved to Article 100, and Article 100, the .2 sections now usually reflect information on reconditioned equipment. Right? Now, as far as the different parts in Article 100, they were done away with. If you remember in the 2020 code, Part 1 was general definitions, Part 2 was for definitions over 1,000 volts, and then Part 3 was for hazardous classified locations. Well now, here it is, almost 900 definitions, and they're just simply in alphabetical order. One of the other things that they've done in the code is that you'll see in parentheses after the definitions another term. So it may say cable, medium voltage, and then in parentheses it'll say medium voltage cable. At first I thought, to be honest, that was a little weird, but actually it works pretty well. If you're online and you're searching on the NFPA link website, for example, for a particular term, you type the term in rather than have to type type in the comma, cable, comma, medium voltage. You just type in medium voltage cable, which you're looking for, and the answer will pop up for you. So anyway, that's actually been pretty helpful to me, I've found out. The new definitions, a few of the new definitions, and I'll give you the ones that I kind of am partial to anyway. So, energized, likely to become. So, something that's likely to become energized. We use that term all of the time, don't we? We say that the term, if you think of ground faults, okay? Ground faults. So we have to bond to all of these metal components, don't we? Any normally non-current carrying metal component that's likely to become energized during operation, we have to bond to it for safety. And so we've never had a term for likely to become energized. And what it talks about is breakdown of insulation on the conductor, on the ungrounded conductor, then that other grounded conductor that could cause a ground fault. And so anyway, now we have a term for definition for likely to become energized. Then load management. The idea of load management, we see more and more of this, don't we? We need to what? We need to control the loads, is what it's talking about in a particular facility maybe for energy management. Also, if you look under PV, you'll see PV DC circuits. And then it's actually broken down and underneath that PV DC circuits into 2 separate definitions. One for source PV DC circuits and one for string PV DC circuits. So anyway, if you do work with the photovoltaic systems, look under PV in your code book and take a look at some of those definitions. Now, we have a new term for a restricted industrial establishment. And what a restricted industrial establishment is, one, it only applies to hazardous classified locations. So that means it only applies to those locations in those articles in Chapter 5 addressing hazardous classified locations. And the definition of restricted industrial locations, no access to the general public, right? That makes sense. And also all of the equipment is maintained by qualified personnel. And don't confuse that with supervised industrial installation. And then we've had for the last, couple editions anyway, we've had definitions for reconditioned equipment. Reconditioned equipment. And so there was some confusion. People said, hey, is that the same thing as doing my routine maintenance on equipment? Well, no, it's not. There's a definition for servicing equipment. So if you look at that definition for servicing, it's what we would think about as routine maintenance. Low voltage power circuit breaker. We rack it out, we inspect it, we do some tests on the contacts, we maybe lubricate, visual inspections and so forth, and maybe some secondary injection tests or whatever. Routine maintenance items, and then we rack it back in. As compared to taking that breaker out, sending it to a rebuild facility somewhere, and they completely tear down every stinking part on that breaker, don't they? And if something's getting worn, they replace it. They might replace springs and so on and so forth. So anyway, they completely rebuild that breaker and put it in like new condition, is the way I think of it. So the difference between reconditioned and servicing. Now, if I'm going to service equipment, I service my equipment, right? NFPA 70B now, the standard for electrical equipment maintenance, I follow that. If I'm going to recondition it, remember there are requirements for labeling on that equipment. So you'll want to take a look at that. So those are some of the new definitions that we have in Article 100. Another thing I want to clear up is voltage levels in the NEC. And I think where people get confused on the different voltage levels is they try and read things into the NEC. The National Electrical Code does not specify the different voltage levels for our systems and equipment. It's pretty specific on what it specifies as voltage levels. There are 6 different definitions regarding voltages in the NEC. And some of them we're familiar with, right? Like the nominal system voltage, the voltage assigned to the system. We do have a definition for high voltage. High voltage, it says it's the potential difference of more than 1,000 volts nominal. Say, oh, okay, that's high voltage. And you say, no, that's not, that's medium voltage. And on it goes, right? But just read in the code book. It says high voltage, as far as they're concerned, a potential difference of more than 1,000 volts nominal. And that applies throughout the code. Now, there's an interesting informational note underneath that definition where it says that 1,000 volts up to 52 kV are commonly, 52 kV are commonly referred to as medium voltage. How many of you have 52 kV systems inside your facility? If we take a look at the IEEE C37 standards regarding switchgear, we'll find some information on medium voltage switchgear. Medium voltage switchgear is generally rated at either 5 kV, 15 kV, 27 kV maybe, or 38 kV. And usually that's at least as high as I've seen on medium voltage switchgear, and we call that medium voltage. So in a 5 kV switchgear, we'd put 4160 nominal system voltage, and 4160 breakers, we'd call them, though they're rated for 5 kV and all of that. So anyway, a little bit of confusion there with the high voltage. But once again, if the code somewhere under equipment or wherever talks about high voltage equipment, whatever it is, it's talking about something being rated more than 1,000 volts. Okay? Potential difference of more than 1,000. Now, low voltage is also defined in the code. However, you got to be careful. It says low voltage is 24 volts. However, it only applies to Article 551 for recreational vehicles. So I can't go around throughout the code and say, oh, well, the code says 24 volts is low volts. No, it doesn't. It doesn't say that at all. In Article 551, low voltage is 24 volts. It's interesting if you look up nominal voltage, and it gives the definition, the voltage assigned to a system. And then there's an informational note, and it's going to refer you to an ANSI IEEE standard, the C84.1 standard, which is the voltage ratings for electric power systems and equipment. So that's where we go to actually find the voltage classifications on our system. So for instance, we could look up and we'd say that we'd find that according to the IEEE, medium voltage systems go all the way up to 100 kV. However, I can't buy 100 kV switchgear, right? Metal-clad switchgear to put inside of my building. I don't think, right? It's not going to be medium voltage equipment. So anyway, you might want to take a look at that ANSI C84 standard then if you have any questions about the classifications of the actual voltage level of the systems. You don't find this information in the NEC. There's another interesting definition. I just told you low voltage, according to the article on recreational vehicles, is 24 volts. There's another definition for low voltage. It says the low voltage contact limit. And it applies only to Article 680, swimming pools, fountains, similar installations. It says that, and that actually specifies 4 different voltages, and they range from, I think it's about 15 volts up to 30 volts, okay? So anyway, so pay attention to that, but that only applies to Article 680, low voltage contact limit. And there's another definition in the code for low voltage suspended ceiling. Low voltage suspended ceiling power distribution system, Article 393. And it says that it must be supplied from a Class 2 power supply. Then there is a definition for maximum voltage, but it only applies to wind turbines, Article 694. So pay attention to your definitions on voltage and don't get confused. We're going to look at some different cables next. There are 44 different definitions for cables in the NEC. We're for sure not going to go through all of those, okay? What's interesting is there is no definition for cable itself in the NEC. If we take a look at some specific definitions like the IEC, which defines it pretty well, it says it's an assembly of one or more conductors or optical fibers with a protective coating and possibly a filling, insulating, and protective material. But we'll talk about a couple more, but there are 44 different ones. Now, if we look at, we can find, here's some type NMB cable, right? And so we know from the color coding, this is going to be number 10. And so this is type NM non-metallic sheath cable, type B, and suitable only for dry locations and so forth. If it's NMC cable, that means the outer jacket is corrosion resistant. Here's another cable you'll find in those 44 definitions. This is some circuit integrity cable. If I look at this, it's got the jacket on the outside. That's pretty stiff. Okay, it's pretty hard. And then I've got some insulation, but when I take off the insulation, there's some glass material, some like fiberglass material wrapped around the conductor. So if I take a look at the ratings on this cable, 16 gauge FPLR-CI, the CI tells me it is circuit integrity cable according to the definition. And it is 2-hour fire resistive cable. And then it goes on from there. So anyway, circuit integrity cable, 2-hour fire resistance. Many of the other cable definitions we're familiar with, type MC metal-clad cable, AC armored cable, and so on and so forth. There's a definition for abandoned cable, and it just says it's not terminated, other than it might be in a fitting at its box or enclosure or wherever it's going, but it's not terminated inside the enclosure. It's been in its tag is not identified for future use. If so, by definition, that's an abandoned cable. But if you take a look, the information you'll find on when we have to remove abandoned cable or mark it for future use or whatever, you'll find that in chapters 6, 7, and 8. You need to go to the individual articles. You won't find information for removing abandoned cable in the first 4 chapters of the NEC. 31 different types of cable, a cable bundle. So I take and I group my cables together for how long? At least 40 inches. If I don't have 40 inches, I don't have a cable bundle. Informational note tells you to be careful if you're going to do that, because you can cause overheating problems, can't you? Medium voltage cable. Now there's a definition for medium voltage cable, and it says cable that's rated from 2001 to 35,000 volts. Now that's kind of interesting if you think about your definitions. I just told you high voltage is anything greater than 1,000 volts, and now we've got medium voltage cable 2001 to 35,000 volts. And medium voltage cable is obviously constructed differently than normal cable. Here I've got a single conductor. This happens to be a copper conductor. I've got an extruded semiconductor. It's a black layer. You can barely see it underneath the white insulation that you see. The whole idea with medium voltage cable is I create a lot of voltage stress. Voltage is a pressure, isn't it? It's an electromotive force. And it's going to try and move molecules of insulation out of the way. It can punch through that insulation and so forth. So we need to relieve those voltage stresses. So we do that with a semiconductor layer, one that's extruded right over the copper conductor itself. Then there's the insulation, and then there's another semiconductor layer. Then I have the copper tape that's wrapped around the entire conductor. The purpose of the copper tape, we're going to ground it probably at both ends, because the way I look at it is you can't keep all the electrons on the inside at medium voltages. You're going to have some of those escape, and you could create a potential difference. So you're going to take this metal sheath, allow any conductors that do escape, they escape into the, or any electrons. So the way I look at it, that do escape, they go into the metal sheath, it's connected to ground, and that potential difference then is dissipated into the earth. Medium voltage cable, 2001 to 35,000 volts. Let's talk about circuit breakers a little bit, different types of circuit breakers. There are 4 different types of circuit breakers identified in the NEC. It talks about adjustable circuit breakers. It talks about instantaneous trip circuit breakers, inverse time over current breakers, and non-adjustable circuit breakers. So first of all, a breaker, standard, standard 20 amp circuit breaker, molded case because it's all in molded plastic case, right? And I take a look at this, and it is called an inverse time circuit breaker, meaning that the more current that flows, the faster it trips, which is what I want. So 20 amps is what's on the handle, meaning that it's rated to continuously carry up to 20 amps of current flow. I don't want to exceed any temperature limitations on the breaker. It gives me the type breaker. It has an interrupting rating of 10,000 amps. Interrupting rating. How much current can this breaker open up under a fault condition and not have any physical damage to it? Okay? That's my interrupting rating, kind of in a nutshell, if you look at the definition in the NEC for interrupting rate. So this is an inverse time circuit breaker. We have other types of circuit breakers. For instance, this is an instantaneous circuit breaker. It has no inverse time feature to it at all. It builds up to a certain value and boom, the breaker trips. And that's it. So we use this breaker for short circuit and ground fault protection. In fact, we may often call this breaker in many applications, we'll talk about it up here on the board behind me in a minute, about what a motor controller is and a combination starter. But this particular breaker, it only has instantaneous trip, but the instantaneous trip is adjustable on this one. And it is, all it sets is the pickup value. It does not set any time delay. No intentional time delay, but I can set the pickup values on this particular breaker. Often referred to as motor circuit protectors. Let's take a look at an example back behind me. This is an inverse time circuit breaker, so we might call it a motor circuit protector. One of the definitions, one of the terms that we run into a lot in the world of motor controllers is we talk about combination starters. And people say, oh, it has to have fuses. You got to have a disconnect switch or whatever it is. And the answer is, well, no, not really. You don't find all of this information in the NEC. But there are different types of motor starters. This is an older style because I have the circuit breaker and then I have the motor starter down below. So there are 4 requirements to be a combination starter. To be a combination starter, I have to have a disconnect. So I've got my disconnect, and that is my circuit breaker right here. So I can open and close the circuit breaker handle. That becomes my disconnect switch. I've got short circuit and ground fault protection. That's requirement number 2. And where is that? Well, that's inside of the circuit breaker. It's an instantaneous trip circuit breaker, short circuit and ground fault protection. Certain large amount of current flow causes the breaker to trip instantaneously then. And then the next requirement is I have to have some way to start and stop my motor. So inside of my starting contactor, I have some contacts. When I energize the coil that controls the motor starter, it of course closes the contacts, and that allows current to flow to the motor. The fourth requirement to be a combination starter is I have to have overload protection. So I have overload protection down here on the bottom of what we call the starting contactor. When they manufacture the starting contactor and the overload relay together, the whole unit is called a motor starter. And if I provide my short circuit and ground fault protection and disconnect switch all in the same configuration like this, then I have a combination starter. But there are different types of combination starters. You may see something like this inside of a motor control center. You may see a similar arrangement inside of looks like a disconnect switch, larger than this one, but it'll be a fuse disconnect. So instead of a circuit breaker, I have a fuse disconnect. The fuses supply my short circuit ground fault protection, and then I have my entire motor starter with my contacts and my overload protection anyway in it. So just a little clarification maybe on that concept. That term combination starter always seems to be a little confusion on that. Now let's talk about fuses. There are 6 different definitions of fuses. First of all, it's kind of nice. It gives us a definition for a fuse. It says it's an overcurrent protective device with a circuit opening fusible part that is heated and severed by the passage of overcurrent through it. So for instance, here's a power fuse, power circuit fuse. The definitions, there's a definition for fuse. There are electronically actuated fuses. There are expulsion type fuses that you'll see in your medium voltage systems up on a pole somewhere. And when the fuse blows, it actually forces gases out a hole in the bottom of the fuse. And when those gases come out, that's what actually extinguishes the arc on the inside. I can have vented fuses or non-vented fuses. This particular fuse is a power fuse, right? And I take a look at it, and it's a energy efficient, dual element time delay class RK5 fuse. Well, the R in the classification tells me that it has a rejection feature on it, so I can only put it in a fuse clip that will allow this particular type of fuse to go in there. This is a 30 amp fuse. It's a time delay fuse. So what that tells me is I could use this on something like a motor or a transformer. If I have a short circuit or ground fault, large amount of current flow, the fuse opens very quickly. However, when I first energize that motor or transformer, I get a large inrush current. The fuse doesn't blow. On this particular fuse, we'd need to look at the time current curve on it, but it's rated for 30 amps. So it might allow 150 amps for 10 seconds before the fuse would blow. And by then, certainly the motor running current, transformer, inrush current should all go back to normal. And then the fuse stays in the circuit for my short circuit and ground fault protection. So different types of fuses. So get some confusion on that, take a look at your definitions. Pretty well self-explanatory on that. There are different classes of circuits, right? We've always, for a long time anyway, we've had class 1, 2, and 3 circuits. And there what we have to do is we look at the power supply. And the conductors from the load side of the power supply out to where we utilize that power, utilization equipment, we call those the circuit conductors. So if it's connected to a class 1 power supply, it's a class 1 circuit. We see a lot of class 2 power supplies, don't we? So those circuit conductors become the class 2 circuit conductors and so forth. And then the same is true with class 3 power supplies. For the 2023 code, as you're probably aware, there's a new definition for class 4 power circuits. And these are also called fault managed power circuits. And it only applies to Article 726, which is on fault managed power systems. And what it is it's a newer technology, and where we take the electricity, and rather than just send the electricity out to the load, we divide it up into packets. And then we send those individual packets out to from a transmitter out to a receiver, and then the receiver takes and sends the power out to the load. Up to 2 kW I've seen so far, so that's a pretty large system. And it's like I say, it's a newer technology. I'm sure we'll see more of it. It's very efficient and it's very safe. It's much safer than just supplying a whole lot of power as we normally do down a feeder circuit or whatever. So anyway, be aware of Article 726 and the new definition there on a fourth class of circuit. Grounding. Finally, let's wrap up with grounding then and take a look at some of the different grounding terms that always provide us some confusion, huh? There are 17 different definitions when we look under grounding. And if we're going to talk about grounding, we've got to talk about bonding, don't we? So let's clear that up a little bit right now. The difference between grounding and bonding. If I connect something to the earth, that's grounding. I may connect this grounding electrode conductor to a piece of rebar that's in the concrete. So it extends the connection from the earth up through the concrete where I can connect my grounding electrode conductor. That's ground. I intentionally connect to the earth. That's grounding. Now, bonding I use for protection against ground faults. Any metal component that's likely to become energized during operation, we saw a new definition for that, okay? I have to bond to it. So when I bring in if I'm going to put some device in this box and now connect this box or mount my box and connect whatever's on the inside back to my power circuit, I have to take this equipment grounding conductor, right, and I'm going to run it all the way back, and it's going to connect to the equipment grounding bus bar, which is bonded to the neutral bus bar through the green screw, which is the main bonding jumper. And that way, I'm going to carry any fault current all the way back to the source, back to the transformer, back to the neutral. And when that happens, if I've got low impedance in that circuit, the circuit breaker goes ahead and trips and clears the fault for me. Also, what that bonding does, by connecting this box to ground, what have I done? I put this box as the same potential of what I'm standing on. So if the box should become energized, the box and me are both at the same potential. I don't get a shock. I like that idea. And then the breaker trips and clears the fault for me. So just some differences there on grounding and bonding. Always seems to be a point of confusion. Ground fault circuit interrupters, GFCIs. Remember, there are two classes of GFCIs we generally talk about. We talk about Class A and Class B. Class A is the one we use for personnel protection, trips at 4 to 6 milliamps. And remember, ground fault protection of equipment, which is defined in Article 100, is totally different from my ground fault circuit interrupters that we use for personnel protection, okay? Ground fault protection of equipment, a system intended to provide protection of equipment from line to ground current sent. Right? And so we usually have we'll have some type of relay, protective relay, in order to protect our equipment should we get a large ground fault. Well, we're out of time again today. So anyway, go back, look at your definitions in Article 100. Make sure you understand all those different terms and don't get confused with things like voltage levels and so forth and grounding and bonding and all of that. Take a look at some of those new definitions. In the meantime, work safe. We'll see you at the next Tech Talk.